trigonometric functions of acute angles. And a major focus is going to be on what are the nice ones. And the nice ones are the ones you learn about in geometry, the 30, 60, and 45-degree angles. So we want to use right triangle trigonometry. We want to work with the two famous triangles, the 30, 60, 90 triangle and the 45, 45, 90. And we will eventually evaluate some trig functions with the calculator just so that we get a feel for what they look like. And then apply right triangle trigonometry to solve right triangles. And that's probably tomorrow's stuff. So we start with right triangle trigonometry works on the principle that triangles are similar. So any 30, 60, 90 triangle has the same shape as any other 30, 60, 90 triangle. It's just one's going to be bigger than the other one, that's all. Any 45, 45, 90 triangle has the same shape as another 45, 45, 90 triangle. It's just going to be bigger. So what that tells us is all the angles are congruent, but the corresponding sides would be proportional, you know? Because we'd be taking something and blowing it up just like you would blow up a picture if you went to Target and said a little machine or Walmart and said, hey, make this 120% of what it is before. What the machine does is it takes 1.2 times all the stuff you have on there and it makes it bigger. That's what happens when we talk about similar triangles. One of the most basic similarity postulates was angle-angle. And what that said was, if you knew that two triangles had two sets of corresponding congruent angles, you could automatically know that they were similar. And that's because every triangle has 180 degrees. So if they already have two angles that are the same, the third one automatically has to be the same by subtracting from 180. Therefore, we only need to know one set of acute angles are congruent in order for the triangles to be similar. This one acute angle determines the 6 trig ratios for side lengths of a triangle. And again, this has been around for thousands of years. It used to be really thick in the back of our books, all the trig tables that were back there that have been figured out long ago. To make our computations easier, we often use acute angles in standard position in the xy plane with the vertex at the origin. We want to connect this up with what we already know, which is positive x-axis is where that initial side is going to go, which is array. And then we're going to have a terminal side. And we want to think about how all of this is going to form a triangle. And some of you had asked before about the reference triangles and said, why the x-axis? Why do we always do that with the x-axis? Because that's the way we form a right triangle, is going to be with that reference angle. And that right triangle has trig that we already know from our past, so we can connect that to what we know and go from there. And no, it doesn't matter if it's over here for your terminal side or over here. We're always going to form that triangle with the x-axis. And the reason we do that is because its coordinates then help us with what's called coordinate trigonometry. So that's the reason we do that. An acute angle theta in standard position with one ray along the positive x-axis and the other extending into the first quadrant. We would love it if everything's in first quadrant. That's not reality. But in first quadrant, everything's positive, so we don't have to do too much thinking about signs when we're in there. Now, get past my homework stuff there. We've got opposite, adjacent, and hypotenuse. Do you remember SOHCAHTOA from way back when? Okay, because that's really, we're going to just be reviewing a lot of SOHCAHTOA. That's really what we're doing today. Not a lot of new material in here. So SOHCAHTOA helps us as a mnemonic device to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So those are the three primary trig functions, sine, cosine, and tangent. But we also have the reciprocals, and we're going to have to learn those a little bit better than we did in geometry. Most of the time we could make our way through what we needed to by using one of the primary three instead of the secondary. But some of the things we're going to do in here are going to require us to know, hey, when you flip, when you take the reciprocal of sine, you get cosecant. When you flip cosine, you get secant. When you flip tangent, you get cotangent. And some people will have a lot of trouble figuring out cosecant and secant. Don't be one of those people. Notice between these two pairs of names, there's 3 pairs here, any two only gets to use the co once. So sine still needs a co. it's cosecant. Cosine already has a co. You can't use it again. It's going to be secant. And then tangent, you're going to need a cotangent. So if you're ever thinking, okay, which one is it again that gets cosecant and secant, just remember, with any pair, you can only use the co once. So sine and cosecant, cosine and secant, tangent and cotangent. And again, all of this is based on our SOHCAHTOA from way back when. And one of the things we had to do way back when, that we're going to have to do now, is if any piece of this is missing, we have to know how to find it. You know, if they give us the hypotenuse and the opposite side, we have to know how to find the adjacent side. And that's just going to be the Pythagorean theorem. That's all that is. A squared plus b squared equals c squared. So down here, it says, there are twice as many trigonometric functions as there are triangle sides to define them. So we can already explore some ways in which the trigonometric functions relate to each other. During this exploration, we'll help you learn which ratios are which. So number 1 says, each of the 6 trig functions can be paired to another that is its reciprocal. Find the 3 pairs of reciprocals. Okay, so we've got sine of theta, and I'm just going to label this reciprocal and make a little chart here. What's the reciprocal for sine? Cosecant. And if we have cosine, what's its reciprocal? Secant. And if we have tangent, what is its reciprocal? Cotangent. Now, if we realize, hey, sine, that's always going to be opposite over hypotenuse, so a little O over H, then we immediately should say to ourselves, well, if cosecant is a reciprocal, doesn't it have to be H over O? Absolutely. It has to be the reciprocal. Cosine is adjacent over hypotenuse, so H over H. Well, that means secant has to be H over A. Tangent is opposite over adjacent. So that makes cotangent adjacent over opposite. I am not a memorizer. I'm not. I try to think logically about everything that I know in math. And so I did memorize SOHCAHTOA. But from there, I'm always thinking, what do I know about those? How can I use that to find the secondary trig functions? So I think, okay, if I need cosecant, which one does that go to? That goes to sine. If I just flip sine, then I'll have it. And go through those steps. 2 says, which trig function can be written as the quotient of sine of theta over cosine of theta? Sine of theta over cosine of theta. Well, that doesn't help me, because everything that's up there is opposite, hypotenuse, adjacent, all that good stuff. Oh, but I know sine is going to be opposite over hypotenuse. And I know cosine is adjacent over hypotenuse. Now it just looks like a fraction. So we don't divide fractions, we multiply by the reciprocal. So let's see, that would be opposite over hypotenuse times hypotenuse over adjacent. Well, hypotenuse is going to cancel out. And I get opposite over adjacent. Which trig function is opposite over adjacent? We found our answer. So what we just did was we used the definitions. The definitions are when you talk about opposite, adjacent, and hypotenuse to figure out how does that work with all of these trig functions. And then number 3 says, which trig function can be written as the quotient of cosecant theta over cotangent theta? Do the same thing. Find that trig function. Haven't already? Which one? Secant? So there's a lot of playful algebra you can do with the trig, knowing those definitions. And then 4 says, what's your simplified product of all 6 trig functions multiplied together? Interesting. Let's see. Opposite over hypotenuse for sine. Adjacent over hypotenuse for cosine. Opposite over adjacent for tangent. And then flipping sine to get cosecant would be h over o. Flipping cosine to get secant would be h over a. And flipping tangent to get cotangent would be a over o. Do some canceling. What is it, everybody? It's 1. That's a pretty cool property right there. Multiply all of those 6 trig functions for any theta, and you'll get a 1. Number 5 says, which 2 trig functions must be less than 1 for any acute theta? Hint, what is always the longest side of the right triangle? Let's make that theta. If that's theta, as far away as I can get from it is its opposite side, which will be over here. And the side that's right next to it gets adjacent. Well, what's the other one? Hypotenuse. The hypotenuse is always what? The longest side. Now, technically, the definition doesn't say the longest side. The definition says the angle opposite the right angle. But it has to be the longest side because that's the biggest angle. It has to be. So if we're going to put opposite over hypotenuse, won't that always be a fraction between 0 and 1? Because you've got a smaller side over a bigger side. How about adjacent over hypotenuse? Won't that always be smaller side over longer side? How about opposite over adjacent? Are we guaranteed that adjacent is going to be longer than opposite? Do we need to do any more? Because if we flip it, then the hypotenuse will be on top. So which trig functions are these 2? Sine and cosine. Those are the ones that will have some side of the triangle over the hypotenuse. And the hypotenuse is always the biggest side. So cosine and sine have to be between 0 and 1. Now technically we could have negatives in there too, but we're not going there right now. Remember the sine? Hopefully you do. Some of you probably had a geometry teacher that didn't sing. But singing helps you remember the 30, 60, 90, and 45, 45, 90 triangles. So 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in the triangle game. Yeah. You remember them. Just works. It does. Through a song. I have extra copies of the song. I know it's in your notes, but I have extra copies. Because this is definitely what we need in this chapter. We have to understand the relationships between the sides of these triangles in order to do right triangle trig. So, theme of Take Me Out to the Ball Game, by the way. That's how we sing that one. And that'll get you all of those sides that you need. So, like it says, every student of trigonometry should be able to find these special ratios without a calculator. We don't want decimals. We want exact solutions. That means you have to be able to recreate those at the drop of a hat. And actually, if you can do that, trig is going to go so much easier for you. everything we do with trig will go so much easier for you if you could sketch those triangles right away. Like I said before, I took college trig because I wanted to get an in-depth feel for it before I had to teach it. That is what got me through the whole course. Just constantly being able to recreate the 30, 60, 90 and the 45, 45, 90 triangle. And then there's no more memorizing because you just think your way through it. So this says we're going to find the values of all 6 trig functions for an angle of 45 degrees. And you can either sing the song or you can remember the 1, 1, square root of 2 relationship. Now that doesn't mean every 45, 45, 90 triangle has sides of length 1, 1, and square root of 2. What it means is they're proportional to all of the triangles that would. So if we want 6 trig functions for a 45-degree angle, it doesn't matter which of these 45-degree angles we use. I'm going to call that one theta right there. But what matters is our labels, our opposite and our adjacent and our hypotenuse. This is as far away as I can get, so that's opposite. This one is right next to it, and that's what adjacent means. And this is the hypotenuse. So I'll just use those to figure out what the 6 trig functions are. So the sine of 45 degrees equals, well, sine is opposite over hypotenuse. So that will be 1 over the square root of 2, which we absolutely will not leave. The book does. We are not going to do that. And that's because as soon as we do that, you're going to have the professor at college that tanks you on everything because you did not rationalize the denominator. These are exact, and we should know these. So we're going to multiply by the square root of 2 on the top and the bottom, and that'll be the square root of 2 over 2. It also helps you with understanding when something pops up on your calculator that you've seen it before. Hey, that's a number I should know. And then cosine of 45 degrees is going to be adjacent over hypotenuse, which again is 1 over the square root of 2. So we can just cut to our answer, square root of 2 over 2, because we know that's going to be the same. And then tangent of 45 degrees is opposite over adjacent, which is going to be 1 over 1, which is 1. And then we need to do some flipping. So sine, what's the reciprocal again to sine? Cosecant. So I would go right back to the very first thing that was sitting here, 1 over the square root of 2. Flip it, square root of 2 over 1. It is the square root of 2. What do you get when you flip cosine? Reciprocal of cosine? What's the reciprocal of cosine, everybody? Secant. So the secant of 45 degrees, square root of 2. And then cotangent, pretty obviously, going to end up being 1. So flip sine, you get cosecant. Flip cosine, you get secant. Flip tangent, you get cotangent. And again, even just showing that little bit of work helps you when you have to flip it to find, oh, what did I flip originally before I had to rationalize the denominator and make that the square root of 2 over 2. For any right triangle, if we know 2 sides of the triangle, how do we find the third side? I mentioned this earlier. What do we use? The Pythagorean theorem. Good old Pythagoras. A squared plus b squared equals c squared, where c is the hypotenuse. C is the hypotenuse. So this one says we are going to evaluate trigonometric functions of 30 degrees. Find the values of all 6 trig functions for an angle of 30 degrees. 30, 60, and 90. It's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3. So we want the 6 trig functions for 30 degrees. This time I can't pick my 30-degree angle. My 30-degree angle is right here. This does not have 2 30-degree angles, like 45, 45, 90 did. So now I label opposite, right next to hypotenuse. So then we need the sine of 30 degrees. What's the definition of sine? Opposite over hypotenuse. 1 over 2. Cool. 1/2. Cosine of 30 degrees. Definition. Adjacent over hypotenuse, square root of 3 over 2. Tangent of 30 degrees, what's the definition? Opposite over adjacent. Rats, got a little work to do there. 1 over the square root of 3, but it's not awful. We'll just multiply by the square root of 3 on the top and the bottom. Square root of 3 over 3. And then you just flip it for the others. Secant would be 2. Secant would be 2 over the square root of 3, which we know we can't leave. So we're going to multiply by the square root of 3 on the top and the bottom and get 2 square roots of 3 over 3. And then cotangent, go back to the beginning and say, oh, that was 1 over the square root of 3, so it'll be square root of 3 over 1. And we've got it. Used a ton in trigonometry, the 30, the 60, and the 45. So we need to be able to reproduce those and reproduce them quickly. Next up, oh, this is looking complicated. We got triangles within triangles here. Yep, that's because this is an equilateral triangle. Equilateral, back from geometry, equal sides. So that makes this 60, 60, and 60. And look what they did. They broke it into 2 triangles. Well, that would make those 30, 60, 90 triangles. So an altitude to any side of an equilateral triangle creates 2 congruent 30, 60, 90 triangles. If each side of the equilateral triangle has a length of 2, then the 2 triangles would have lengths of 2, 1, and square root of 3. So we see that same relationship from the song in the 30, 60, 90. And just in an equilateral, we're going to be able to have 2 of those. There will be 2 of those 30, 60, 90s. Now, a word about radical fractions. There was a time when 5 square roots of 11 over 11 was considered simpler than 5 over the square root of 11 because it was easier to approximate. But today they are just equivalent expressions for the same irrational number. And I'm going to tell you, the book was just lazy. So when they put 5 over the square root of 11, I expect you to have the answer 5 square roots of 11 over 11. And that's because when you go to college, practically nobody is going to let you get away with this. Anybody that's been teaching within the last 10 years will not let you get away with that. You will have to radicalize that denominator. So rationalize that denominator and get that looking at 5 square roots of 11 over 11. With technology, either form leads easily to an approximation of 1.508. But most of the time when you're using the special triangles, you don't want approximations. You want a perfect answer. So no matter who you had teach in second semester, we're going to tell you rationalize the denominator for these. Then down here, it says the one we have left is 60 degrees. We did the 30, we did the 45, evaluating the trig functions of 60 degrees. Find the values of all 6 trig functions for the angle of 60 degrees. Note, most of the preliminary work has been done in example 2. Well, that's because we already had the triangle. 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3. That's what we need. It's the same one. Now we're at this angle. And we have to label. So as far away as we can get, opposite, right next to it, adjacent. The one that's opposite the 90-degree angle is the hypotenuse. We need sine of 60 degrees, cosine of 60 degrees, tangent of 60 degrees, and then we'll just need to flip them. Sine of 60 degrees. What you got? Square root of 3 over 2. Yeah, I already know your heads were down and everybody was already doing these when I was writing this down. Cosine of 60 degrees. What do you have? 1/2. Tangent of 60 degrees. Square root of 3. So what's the cosecant? Louder, please. Cosecant 2 square roots of 3 over 3. Secant, 2, cotangent, square root of 3 over 3. Hey, wait a minute. Those look really familiar. Where's our 30-degree triangle? Back here, wasn't it? You say on the page we were just on. Aren't these the same numbers? 1/2 square root of 3 over 2, square root of 3 over 3, 2 square roots of 3 over 3, and the square root of 3. Aren't those the same numbers we just got? Are they in the same places? They're the same numbers. And that's because it makes perfect sense. They're in the same triangle, for goodness sake. It's just you're changing your reference from which angle you're working with. And that actually brings us to the definition of complementary. Sine and cosine are said to be complementary in that 30, 60, 90 triangle because you'll notice they reversed when you look at what we had for our 30-degree angle. So, number 2 says, compare the 6 function values for 60 degrees with the 6 function values for 30 degrees. What do you notice? They are the same numbers. They are the same numbers, but they're definitely in different places. Because the sine of 30 degrees came out to be the same thing as the cosine of 60 degrees. And the cosine of 30 degrees came out to be what for 60 degrees? Sine. Notice how they add to 90 degrees. Sine to cosine, cosine to sine. Then we had the tangent of 30 degrees. What did that end up equaling? The cotangent of 60 degrees. So again, that complementary relationship between those two. Now we could go ahead and do the secondary ones as well. So cosecant of 30 degrees equaled what for 60 degrees? Think sine and cosine, yep, and then you think about their reciprocals. So that will be secant of 60 degrees. How about the secant of 30 degrees? Yep, cosecant of 60 degrees. I'm going to have to read lips. That's what I'm doing so far. Who wants to say this stuff out loud? Then the cotangent of 30 degrees, what does that equal? Tangent of 60 degrees. There they were. Same numbers in different positions. So 3, long-winded. We will eventually learn a rule that relates trigonometric functions of any angle with trigonometric functions of the complementary angle. Recall from geometry that 30 degrees and 60 degrees are complementary because they add to 90 degrees. Based on this exploration, can you predict what that rule will be? Hint, the co in cosine, tangent, and cosecant always comes from complement. That's what they wanted us to notice. That if you have sine, it's going to equal the cosine for its complement. If you have cosine, it's going to equal the sine for its complement. If you have tangent, it's going to equal the cotangent for its complement. So, how can we put that? The value of the trig function for theta foo theta, that's it, for theta. Value of the trig function for theta is the same for or the value of its cofunction. At 90 minus theta degrees. So in geometry, we never talked about cofunctions. But in trig, sine and cosine are cofunctions. Tangent and cotangent are cofunctions. Because that co from complementary tells us that they have to add to 90 degrees. So they get that fancy name, cofunction. And we go through that. Alrighty. This one says, using one trigonometric ratio to find them all. Oh my goodness. Let theta be an acute angle such that the sine of theta is 5/6. Evaluate the other 5 trig functions of theta. Well, we did this back in geometry. We don't know what it looks like. We're just going to make a sketch. We know it's the right triangle. That's what we know. And we know we need to plop a theta on here somewhere. I'll plop it here. I don't care whether or not it's to scale or not. I just know one of those acute angles is theta. And they told me the sine is 5/6. But if I want to know where to place those, I have to know the definition of sine. What's the definition of sine? Opposite over hypotenuse. OPP over H by P. Well, here's my angle. That means as far away as I can get from my angle has to be a 5, because that's opposite. And the hypotenuse, which is opposite the right angle, has to be a 6. But if I want the other trig functions, I have to be able to find that. And usually we don't use x's for these because of the Pythagorean theorem, but it doesn't make any difference what variable you use. Just know that this has to be an A or a B because C is for the hypotenuse. So then we do a little bit of Pythagorean theorem and say a squared plus 5 squared equals 6 squared. A squared plus 25 equals 36. So a squared equals a whopping 11, and a would be the square root of 11. We do that perfect. We don't try to do any goofy decimal stuff with that. We like them perfect. It's called the elegant. All right, so we know what sine is. We're supposed to get the other ones. The cosine of theta. What would you put for the cosine of theta? You're doing all 6 of them, right? You're doing all 6 of them. Yeah, you are. Fine then. I don't need you. I'll write them up here. Let's see what we have. We have opposite Jesus. Square. Feel a little better about trig? Yeah, I think from the worksheet, people were getting kind of scared. But there's a lot of trig that we do know. And when we get to it, we really find out we know a lot of this stuff. We have some background. It's just getting back to that point when we've had a full year off for Algebra 2, and for some of you 2 years off because you had Algebra 2 in college algebra. It just takes a little bit. You get a little rusty. So why not use a calculator? First of all, because we tend to not really know exactly what we're doing when we just punch things into a calculator. Secondly, these have been around for thousands of years. Do we really think we're that much smarter than the people that came up with these thousands of years ago? We've got a calculator. They had to do all this by hand, but they were pretty doggone smart. And so we had perfect answers. Now the dangers of evaluating those trig functions with your calculator, the first one, almost everybody makes the mistake of not realizing if I'm working with degrees, I need my calculator to be in degrees. If I'm going to work with radians, I have to have my calculator be in radians. So it does come down to operator error. We know what it is we're punching in at any given time. So this one says we were supposed to evaluate the sine of 10 degrees, and this popped out right here. Let's see. Sine of 10 degrees, that's degrees, so I need to go down here to where it says mode, degrees, change that, and punch in the sine of 10 degrees. What about this answer would let us know we're wrong? That's a negative. And we're talking about a triangle when we talk about these situations. There shouldn't be a negative there. So if there's a negative, that's your first guess. Hey, it's radius. Got it? Well, this will go really, really fast. So we're not that far behind. And you'll be able to do, oh, come on, smartboard, behave. There we go. You'll be able to do all of these anyway. Just remember, if you're going to punch stuff into your calculator for any of these problems, you want to remember, if I'm in degrees, if the stuff they're giving me is degrees, I need to make sure my calculator's in degree mode. If it's in radians, I need to make sure I'm in radians mode. Oh yeah, a little harder than I expected, so that's good. Lots of review. I do remember it felt like this assignment was a little long. So know that we may get up to you in the next few assignments because those were pretty doggone good. So it just gets those skills back that you were using in geometry.